1 by t square t by dt square equal to 0. So at this stage, in fact, we should not write equal to 0, because if these two are equal to 0, the equation collapses. In fact, we have taken this part to the right hand side, so this is what we get in the end. And another important thing to observe here is, on left hand side it is purely a function of x. Since c is a constant, it is independent of x. On right hand side it is purely a function of time. So these two terms in the differential form can only be equal unless and otherwise both of them is equal to constant. This is intuitively we can say. In fact, in mathematically you can prove that in a differential form, if if see in other words, whatever you do in on this side, you cannot get a function of time, because this part can be purely a function of time, and whatever you do on this side you cannot get a function of x, because this side is a function of x, right? So the only way these two can be equal is when you take four derivatives of w, then it should be equal to w. Both of them will get cancelled. And on the other side, upon taking two derivatives of t of t, you will have to get c square t by t by c square. Oh, sorry, t c square. In that way, it can be equal to c square. So in that way, these two should be equal to a constant, and let us say that is omega square. And now we will go further. So at this stage, we will get two equations, and we will see how. So upon writing c square by w d to the power of 4 w by dx to the power of 4 equal to minus 1 by t d square t by dt square equal to omega square. So these are basically two equations. So we can write, firstly we will assume c square by w d4 w dx to the power of 4 equal to omega square. The other equation that we get is 1 by t d square t by dt square equal to omega square. So these are the two ordinary differential equations that we have got. Please note that a partial differential equation is converted into two ordinary differential equations using a separable form of assumed solutions, right? And here this is the this symbol is omega. So please differentiate between omega and capital W and small w, in case if my writing is a bit confusing. Now we will take this equation, that is c square w equal to omega square. Upon rearranging, we will get c square d to the power of 4 omega w by dx to the power of 4. Otherwise, we will write c square also on this side as 1 by c square omega into omega square equal to 0, right? So let us say that uh, beta to the power of 4 is equal to omega square by c square. So we are going to further simplify this equation using beta to the power of 4. So now this equation will be equal to 0. And please note that this is a function of x. So now this is a fourth order ordinary differential equation, and it can be solved by assuming a solution. Let us say the solution of this equation b is of the form capital C into e to the power of s into small x. Right. Since we have assumed a solution, we can substitute into this equation. So d to the power of 4 into c, capital C, e to the power of s into x minus beta to the power of 4 c s into e to the power of s into x. So if we take derivative 4 times, we will get cs square into e to the power of sx. So it is c into s to the power of 4 e to the power of sx minus beta to the power of 4 c e to the power of s equal to 0. Since s to the e to the power of sx cannot be equal to 0, we can take it common and it will cancel out, and c as well. So finally you will get an expression like this. What is that expression? What is that expression? S to the power of 4 minus beta to the power of 4 equal to 0. This is the expression. Upon solving this equation for small s, because small s is the variable in our assumed solution. So s. So since it is fourth power algebraic equation or bicoordinatic equation, we will get 4 solutions for s, that is beta minus beta I beta minus I beta. This is a standard form for solution of any biquadratic equation, which is a very well known and basic thing. So in this way, we have got four solution. Four solution for this equation, which will give the final solution of w of x as c1 e to the power of beta x plus c2 e to the power of minus beta x plus c3 e to the power of I beta x plus c4 e to the power of minus I beta x. Right. So these are the possible solutions. Hence, each and every expression resulting out of each and every solution of this equation leads to a sum total. If an individual e to the power of beta x is a solution and individual e to the power of minus beta x is a solution, then sum of these two can also be a solution for the governing equation or the differential equation, right? Since we get 4 terms, the algebraic sum of 4 terms is the solution, is the this will give the exhaustive solution for the ordinary differential equation that we have got. And this equation can be rewritten in terms of sines and cosines, and we will see how. So for that, consider sine hyperbolic x, hyperbolic of beta x. Otherwise, let us say sine hyperbolic of beta x equal to e to the power of beta x minus e to the power of minus beta x divided by 2. Similarly, cos hyperbolic of beta x equal to e to the power of beta x plus e to the power of minus beta x divided by 2, right?